surveyed things, okay? But they all fall within that same idea that we put a straw into the aquifer and draw the water off of and figure out how we can either protect that or make sure we get panicky when there's not enough recharge because there's not enough snow melt and so forth. So one of the anomalies is, how do you explain Crater Lake? That's a hydrocrater. That's one that has a central peak. It's up in Oregon. And it's at the highest point. There's really no area above Crater Lake to recharge that basin. So you can have snow melt around the ring, and that'll drain certainly in. There's no other inlets. And yet this lake is fed primarily by underground spring water. Well, spring water is feeding this Crater Lake at the top of the mountains, and that's what this is right here. These hydrothermal springs, warm water is being pushed up from underneath. So how do we explain and how do we tap into that idea? So hydrocraters form because they have a water source, a fault line, and heat. So the fault line can be of either a lateral or a vertical one. The water source is that water that happens anywhere, all the way from the surface, all the way down to thousands of feet deep. And what happens is when the crust is moving, it's creating heat, and there are thousands of earthquakes every day because the moon, as it goes around the earth, is stretching and flexing that crust. Okay, now we all know what tides are. Ocean tides go up and down a foot or two, depending on whether it's a full moon or less, right? But how many of you know that there's earth tides? Some of you probably do. Earth tides mean that the crust of the earth is also going up and down. Kilauea, for example, that island goes up and down about 5 centimeters, something they just noticed maybe within 20 years ago. Now when that goes up and down 5 centimeters, not very much really, except that remember, 10,000 feet of rock moved 1 millimeter will produce enough heat to melt rock. If we're going up and down 5 centimeters every day, we're producing an enormous amount of latent heat that's going to just build and build and build until at some point it releases. Now, it's an interesting point is that Hawaii is right dead center in the middle of the Pacific Plate. It's not on that ring of fire. And so that's a question is, what's causing that particular volcano to erupt there? Where is the heat coming from? So the theory is today it's a magma plume. It's coming up there, and then the plate's been moving across, and it's been causing these volcanoes to grow. But how many of here are engineers, and you know what happens when you stress a steel plate or something? If you're bending a steel plate, what happens right in the middle or that weak point of that plate? That wire that you're bending, right? What's happening when you're bending that wire? You're not putting a whole lot of pressure on that. It's getting really hot, right? So right here in the middle of this specific plate, there's actions going on. 5 centimeters that we know of is going up and down every day, right in the center of that plate, and it's building up an enormous amount of heat. So based on our predictions, we should have seen an increase in seismic activity before this lava flow. Was there an increase in seismic activity before the lava started flowing? There was. In fact, it was a rapid increase. There was quite a bit of seismic activity. Earthquakes were happening. And that was creating enough heat to cause that rock to flow, melt it for a while, and then it'll cool down. So what if we applied that same thing? What if we applied looking for hydrocraters? We need water, we need to look for a fault or fault line, and we need to find a diatreme. So instead of looking for aquifers, what if we started looking for diatremes and for fault lines and looking for areas where maybe we could tap into the Earth's natural pressurized system? Because that crust is flexing right here. That's measurable. It's flexing and it's creating heat. And that heat is creating pressurized water, but the pressure is not sufficient to cause it to blow out. It's pretty deep, but it's still there. So one of the things we can look at is what's going on in Yellowstone. Yellowstone's a big magma chamber ready to blow at any second, right? At least that's what we're told. But what if there is no magma there? What should we expect to find if there's no magma and we have a lot of geyser activity going on? What would you expect to find? Water. A lot of seismic activity, heating water. Where's the most active most active seismic zone in the entire continent of the United States? It just happens to be Yellowstone. Yellowstone is constantly experiencing earthquakes, thousands of earthquakes that are not really even measurable. You can't feel them, but you can see them on the seismographs we have around there. Some of them are big enough. Thousands of earthquakes constantly flexing that crust, causing that geothermal energy. And we know it's connected because earthquakes that have happened in Alaska have affected it, and earthquakes that have happened east of the Rockies have affected Yellowstone. So the distribution of the water in the earth based on current ideas are that 95%, 96% of all the water on the earth today is in the oceans. 2.9% is in the glaciers or polar ice we can't get to unless we melt it, and only 1% is underground water. So we're trying to water our cities with that 1%. That's what all of the water that we're using for consumption today is really that 1%, with 0.009 in the lakes and rivers, right? And we're gonna pump a whole bunch of it over here from one lake, and even less than that in the atmosphere. But what about if we turn this around and we recognize that the Earth is actually a hydroplanet, that there is 100 times more water under the crust than there is on the crust. Instead, we find that there would be 99% of the Earth's water would actually be underground. And only 1% of that water would be on the ocean. Now, there's already quite a bit of science that shows that. So here's New Scientist in January 2017, an article came out that said, Planet Earth makes its own water from scratch. Now, why did they have to come up with the idea that the Earth has to make the water from inside? Because they're in a magma planet paradigm. This magma planet paradigm that shapes all of our sciences today says any idea that I come up with has to be fit within that paradigm. But if we don't have that paradigm, we don't have to make water in the mantle. The water's already there. It's coming from the mantle. This one, deep earthquakes seem to be seasonal. They don't understand why the seasonal nature of our entire Earth, the moon and the sun, create these seasonal activity. We see seasonal activity in geothermal areas like in Rotorua and New Zealand and Yellowstone and all the places that there are geothermal activity, we see seasonal cycles. So if we can put together a way to look at seasonal cycles, find the diatremes of the fault lines, and go into those areas. Now think about what's happening is you've got pressurized water, okay? Pressurized water that can't do anything because it's under too much rock overburden, even if it's on a fault line. If we can drill into that, and just by getting into an area where there's enough pressure, we can actually see, and this is totally theoretical here, but this is the idea that Mark Burr with Primary Water is trying to explore, is drilling into these active seismic zones where you can get into pressurized water and let the pressure start bringing that water up from depth, because we're releasing, as we release that pressure, it actually draws. So instead of having to lift the water from 3,000 feet, we're letting the pressure push that water from 3,000 feet up through these chambers that we already know exist. So here's the hurricane fault right here, okay? And this is where Mark Burr actually sent an email to us a couple of days ago, and he knew he couldn't be here for this, he wanted to be, but he sent an email that said, take a look at some of this, and this is what his initial, just kind of an initial quick survey was of the hurricane fault. So this is the profile. This is 250 meters down and then 500 meters. So this is basically half of this. See that little squiggly line right there? There's that squiggly line right there. Okay? What he's seeing right here is these are potential chambers that water may be present in, deep water. And if we can get into the deep water and find a way to harness that or get into that, then that could be a game changer. Now, this is totally unproven science.
The line down there, the fault line you see on that side is solid rock. On the left is the broken up rock.
This is the fault line right here.
Yeah.
Right.
And he took several readings across the area, and they all showed a little bit of possibility and whatnot. When we got to this spot, and he said, "Wow."
Yeah.
This is.
We made a comment that we definitely need to drill this.
Yeah.
So here's the thing: is just look right here. These are two rocks from two ends of your valley, right here. This is from Santa Clara area. This is on the north end of of St. George, and this sits on top of the sandstone. Now, you were told sandstone is the formation of erosion over thousands of years. All that wind blew from the Appalachians. I'm going to pass this around, take kind of a look at it, feel the difference in those two, and I'll tell you what we think about that. So this erosion process that blew this sand across the continent from the Appalachians and deposited on the Colorado Plateau is the generally accepted consensus of where all the sandstone came from. The sand that forms our sandstone hills. So one of the issues Dennis brought up is that this sandstone, when you break it down and you look at it under a microscope, the grains, those little quartz grains, one, they're consistent size. They're all about the same size. Two, they're clear. So those grains would have had to come from a clear mountain, and they were all the same size. Three, there's no organic detritus in those sandstone formations. You have 1,000 feet of Navajo sandstone with no organics in it at all. It's just pure sandstone. So if that were the case, that were deposited by some wind force that was blown across the continent, it would have carried with it at least something other than just quartz. Now, the sand dunes are of a different nature. And what's interesting about the sand dunes, if you were to take that sand, and you can go to any of the sand dunes around here, you can try this experiment yourself. Go get a bottle of sand from a sand dune and get a magnet, and then put the magnet and shake that bottle and see how much iron's in that sand. Okay? Now there's not that much iron at all in the sandstone cliff, but there's iron in the sand dunes. If that sand was blown here from another place, the sand, those little quartz crystals, besides they're all clear, have a density of about 2.7 grams per cubic centimeter, okay? It's fairly lightweight. The little iron filings in there are twice as dense. How did sand pick up those two particulates, carry them across, and drop them in a sand dune, iron and silicon dioxide quartz, and leave everything else out of the mix? The reason that that's a big deal is because the formation of sandstone and the formation of sand itself, they're similar in origin, but they're slightly different processes that are happening. And have anybody here experienced or watched cheese make, the cheese making process? So, help me if I'm wrong, but cheese making starts out, you put all the milk in a big vat, and it's stirred constantly, and you add a bacteria, okay, and it's going along, and everything's fine, and nothing seems to be happening, and then, all at once, pretty fast, what happens?
Curds.
The curds form. They don't form really slowly, do they? They form almost all at once. It's like you're going along and it just kind of suddenly the whole thing curdles all at once. So when sandstone formed, the majority of that was in a very high pressure, high water silica solution, silica saturated solution under pressure. And there's a process called autogenic formation, so it means it formed in place. Spontaneous nucleation. So across hundreds of square miles, all at once, those sand grains formed probably in a matter of a few minutes. They couldn't grow very far because there wasn't enough silica in the system. They grew until that silica load was used up or expended. Now we showed you a picture up there of a hyperthermal growth process. We took a single seed of quartz, about a ½ inch long, put it in that autoclave and doubled it in size in one day, one 24-hour period. So grew a piece of quartz from about a ½ inch to 1 inch in one day. The size of those teeny grains represent roughly 30 to 45 minutes of growth. So in a matter of minutes, the entire sandstone formations were formed, unconsolidated at this point, but formed all at once. And then pressure, they're still under that pressure. They're no longer growing though, they're still under that pressure. And in that heat and pressure, bacteria that of a certain nature that will live in that heat and pressure will grow. Yellowstone, for example, have you seen Yellowstone? There's Grand Prismatic Spring, which has colors of yellow and green and red. Each of those layers in that spring represent a different bacteria that live at a particular heat pressure. So in other words, if it was a little bit cooler, that bacteria would die. If it was a little hotter, that bacteria would die. If the pressure was a little higher or a little less, that bacteria would die. It only lives in this very narrow zone. So during the flood, there were pressure and heat zones of all different sorts. And this particular zone that allows the microbes that produce iron oxide to grow provide the glue that, with that pressure, heat, and water, creates and cements the sandstone. The sand itself from these sand dunes is formed in the free water and it's falling down on top of it. So there's the same process, but just two slightly different areas. That's all I have to share with you today, unless you have some questions about it. I appreciate your time. Yeah.
Has anyone tried to drill into one of these faults and get the gushing?
Well, probably not necessarily going to be a gusher, although it could be. You know, the guy that discovered oil, he persevered even though everybody told him he was nuts, right? And he was drilling at Spindletop, and he drilled, and then he ran out of money, and he got more money, and he kept drilling a little deeper, and he ran out of money, and he persevered and drilled anyway. And in fact, it was about 60 feet further from where the last guy ran out of money, and he hit a pressurized zone of oil, and that oil spurted more than 100 feet in the air and ran for days before they could contain it. So whether or not we hit pressurized water, who knows? The thing that we want to do is find ways to get into deep water. And Mark Burr right now is in Madagascar drilling and following this whole idea, this idea that he's looking for diatrines, active seismic zones, likely places where water might be.
I think one thing Mark stressed with us as we were out looking is, you know, if you drill just a foot or two to the right of that line, you're going to be in solid rock and you're not going to get anything. You get there, you've got to be pretty specific. He had just a small little instrument. It's the same type thing they use in oil, gas, and in mining. But it took, and it read the movement of the earth, that sound, and produced those the pattern that you see up there. But he did one. We went in just a straight line and took 10 steps and did another one, and so we took a whole line across there. And this was just one line. We didn't really. You were really going to get specific why he did some crossings and tried to find cross faults and other things. But he could do that and kind of narrow it in. So you have to look at the geology. I mean, we were on this was right on the Hurricane Fault line, right when the Navajo Trail comes off down into Hurricane Valley. So, and then we did a lot of cross faults that were coming off there. So that's where he was kind of looking to start with. But I know he said they like to, he's a rock driller, is what they said. They like to get into the rock and into the harder stuff. And he was promoting using a directional drill, I don't know, but anyway, something that cased the hole as you went down, so that if you're in this other type of material, you're excluding all that from what you're going to be getting into, so you just get into the primary water.
So does he believe that these pockets of water are coming from underneath, so once you tap into one of those good pockets of water, you have a good source? Is that what he
Well, he's not actually saying that those are pockets of water. He's saying that those are possible open areas of water.
If there's going to be water, it's going to be in a pocket like that. Just because that's there doesn't guarantee that there's water, but if there's going to be water, it's going to be in one of those.
We have some geologists up in Cedar City that have always, said that the fractured quartz monzonite that we have up there, I don't know what you have down here, but they said there's a lot of it. They believe if you do hit certain pockets, you could have good sources of water. Isn't that what we actually, Cedar City, there's just kind of southwest of Wichita years ago, probably, it might be 6 years ago. We drilled, there's a fault line where they claim there's kind of a perched aquifer, and they had us drill in a certain spot, and we didn't end up with a lot of water, but it could have been the challenge with that is, you know, at some point you run out of money and, you know, you drill and so I don't, but we didn't use this kind of technology either. We didn't have this.
Yeah, this is kind of new technology for water.
Even Mark, the way he's applying the technology he has,
Yeah.
he's applying the technology with a new set of eyes because of the whole idea of these diet trees.